Let's do a couple more examples, but we'll do these ones kind of with broad strokes. We won't look specifically at entries here. So here's what I mean. Let's just say we had a matrix A, which is 3 by 4. So I'm not going to tell you anything else about it, just I'll tell you what the dimensions are. And then same for two other matrices, B and C. So I've got three matrices, A, B, and C, and all I'm telling you are what the dimensions are. And let's say we wanted to compute some products. Let's say I wanted to compute the product AB, the product BC, the product CA, and the product CB. Well, let's do some dimension diagrams to figure out what these would look like. So let's do that over here. So dimension diagrams. Just a reminder that that's what these are that I'm drawing over in the upper right corner. So let's start with AB. Let's jot down A is a 3 by 4, and B, which is a 4 by 7. And I just want to make a comment. For this to actually work, you need to make sure the orientation of the matrices in the product you're looking at, this is the one we're looking at right now, and the way they are oriented with each other in the dimension diagram is the same. So in other words, A is to the left of B in this expression. A is to the left of B in this diagram. So just make sure that that's the case. And then you can check, do the inner numbers agree? Do the number of columns of A and the number of rows of B match? And they do, right? So the answer is yes. So that means this product AB is defined and its dimensions are going to be determined by the two outer numbers, the 3 and the 7. So AB is 3 by 7. Now, what are the entries? Well, you can't possibly know that unless you know what the entries of A and B are. So this is as far as we can go at this stage. Let's look at the other three products. So let's look at the product BC. So I'll put a B there and a C here. So B is 4 by 7. C is 7 by 4. Right? And the orientation BC, B is on the left. B is on the left up here as well. So this makes sense to do this diagram. We can check, are the inner dimensions the same? Yes, they are. So what are the two outer numbers? 4 and 4. That means the dimensions of BC are going to be 4 by 4. So that's how these diagrams will tell you the dimensions. Let's look at the next product, C times A. So I'll put C on the left and A on the right. We've got to jot down their dimensions. So C is 7 by 4, and then A is 3 by 4. And again, make sure the orientation matches. C is on the left, A is on the right. C is on the left, and A is on the right. So check, do these inner numbers agree? And actually, this time they don't, right? Those two numbers do not agree. So what that tells you is that this product is not defined. The CA is undefined. The definition of multiplication does not make sense in this setting because we need the number of columns on the factor, columns of the factor on your left to be equal to the number of the rows for the factor on your right, which that didn't match up in this case, so it doesn't work. What about C times B? Well, the diagram for CB, let's write down the dimensions. So C is 7 by 4 and B is 4 by 7. So do the inner numbers agree? Absolutely they do. So the two outer numbers, 7 and 7, will tell you the dimensions of C times B. So C times B is going to end up being 7 times 7. So one of the things that I'm not going to write anything down about this because we're going to talk more about it in the next section, but notice that when you work, at least when we worked out the dimensions for BC, we got 4 by 4. And then by flipping the order of the factors to write down CB, well, that was also defined, but it was a 7 by 7 matrix. So actually, it's right away, the question of whether B times C and C times B, whether they're going to be the same in this case, is answered immediately by the fact that their dimensions are different. So actually, I will write something down. So note, in this case, BC is not equal to CB. We can say that with confidence without even knowing the entries of either the matrix B or the matrix C. Just the fact that their dimensions are different is what allows us to conclude this. So since they have different dimensions. There will be times when you can multiply two matrices in one fashion and then multiply them in the other fashion, and they will have the same dimensions, but they still might be a different matrix. There's no reason to expect, with the multiplication operation being as complicated and demanding as it was, there's no reason to expect that the order in which you multiply the factors won't matter. And in fact, it will matter. So this is the first example of that having happened, or the first time we've witnessed that, but we'll see that again in the next section with more concrete examples. Okay, so that's the purpose of this was really just to show you how these dimension diagrams can become a habit for you, and you can start any multiplication problem by just doing the dimension diagram to get yourself started off on the right foot. Okay, the next idea I want to discuss is the idea of matrix equations. Matrix equations allow us to use the definition of multiplication, matrix multiplication, which we've just come up with on the previous page, in order to actually write linear systems much more efficiently. So I'm going to illustrate, this works for absolutely any linear system you could ever think of, but just to keep things a little bit simpler for the purposes of what I'm writing here, I'm going to do a system of two equations and two variables, but I'm going to write it as generally as I possibly can. So here is a general linear system in the variables x1 and x2. So that's the first equation. The second equation will be written like this, and there you go. You've got the most general system of two equations in the variables x1 and x2 as you could possibly have. And the first observation we're going to make is that this is equivalent to another equation, a matrix equation, an equation in which the left-hand side and the right-hand side are both going to be a 2x1 matrix. So for the matrix on the left-hand side, I said it's going to be a 2x1 matrix. So I'm going to have two entries, the top entry and the bottom entry. The top entry is just going to be the left-hand side of this equation. It's going to be the left-hand side of this equation here. So I'm going to have a11 x1 plus a12 x2. This should have been a 2 here. This should be x2. Maybe something was up. Okay, so that's a11 x1 plus a12 x2 equals b1. And then a21 x1 plus a22 x2 equals b2. I put an incorrect subscript down here originally. That should be an x2. So you've got a coefficient for x1 and a coefficient for x2 in both of the equations. Okay, so that's the first entry on this 2x1 matrix over here. For the second entry, I'm just going to use the left-hand side of the second equation. So I'll have a21 x1 plus a22 x2. So that is a 2x1 matrix. So this linear system is not equivalent to this matrix. It's equivalent to this equation, which is going to involve two matrices, which are both 2x1. So if these are going to be equal, the things I put here and here had better be equal to what I've already put here and here. So do I have anything that's equal to this and equal to this? Well, these two equations tell me that b1 and b2 will work. So I can go like that, b1 and b2. Okay, so the point here is that these two matrices that are both 2x1 are equal. So I'm going to say these are equal as 2x1 matrices. Okay, so I'm talking about this matrix here and that matrix there. And the next observation I want to make is that this matrix on the left-hand side will actually factor as a product. Okay, and that's exciting, so I'm going to put an exclamation mark. So what do they factor as a product of? Well, I need two factors that I can multiply and end up getting this left-hand side back. So I'm going to tell you what those two factors are right now. And so first, let's start with the left-hand factor. Remember, because every product has a left factor and a right factor, just like all of these. So the left factor is actually going to be a 2 by 2 matrix just consisting of all the coefficients. So I'm going to have A11, A12, A21, A22. So I have a 2 by 1 matrix consisting of all the coefficients from this linear system. So that's the left-hand factor. The right-hand factor is going to be the 2 by 1 matrix consisting of the two variables, x1 and x2. All right, so if I were to multiply these now, I'm just going to use, that's what you often use if you want to multiply two matrices. You can use a dot to explicitly write that you're going to multiply them, or if you want, you could just write them side by side like we did up here, and that's also means multiplication by default. But I just want to write that dot there now. So, well, is this going to work? This is a 2 by 2, and this is a 2 by 1. So if I were to call this a dimension diagram, the inner numbers certainly match up, and the two outer numbers, 2 and a 1, well, that's exactly what these matrices up here were. They were both 2 by 1. So my claim is that if you multiply these two matrices, you're going to get this. And of course you will. Because what happens if I take the first row of the factor on the left and the first, well, and only column of the factor on the right, and I go A11 times x1, A12 times x2, I'm going to get exactly, when I add up those products, I'm going to get exactly this. So that gives me exactly this entry. And the other entry, it's the same thing. Right, I'll use black for this one. If I take the second row of the left-hand factor and I multiply it by the first, again, and only column on the right-hand factor, I'm going to have A21 times x1 plus A22 times x2. That's exactly what this is. It's exactly the second entry in this matrix here. So that's how you can confirm that this product actually gets you this. Okay, so this actually turns out to be really useful, and we can use this now to express linear systems like this much more efficiently. So let's make up some labels. Let's call this the matrix B. And because I don't want it to get confused with a number, I'm going to write, later we'll start calling these vector arrows. And I won't talk about vectors just yet, but for now I'm just going to use the notation. I just don't want this to get misread as a number. So just to exaggerate the fact that it's actually a matrix, I'm going to put this vector arrow. So that's going to be a nickname for this matrix with the two constant terms B1 and B2. This matrix over here, we're going to call it A. And then this matrix here that has the variables, I'm going to call it X. But again, just to make sure it doesn't get confused with a number X, I'm going to put a vector arrow on top just to make it stand out as a matrix. But that's going to be this matrix here, this 2 by 1 matrix. Okay, so that's the notation we're going to introduce. I want to make some remarks now. So the first one is we have a name for A. It's called the coefficient matrix of this linear system. So A is the coefficient matrix of this linear system. So what I'll typically do I'm not going to copy this whole system and write it here just to make this sentence complete. I'll just do this. I'll say it's the coefficient matrix of star, and then I'll label this with a star. So just to make it clear that this is the coefficient matrix of this linear system, right? It's the matrix that has all the coefficients, and nothing else. Right, so that's what a coefficient matrix is of a linear system. We have a name for B as well. This matrix here, it's got all the constant terms put together. So, and it's a column matrix. So I like to call it the constant column. You can call it the constant matrix as well. It's the matrix, which has all the constants put together inside of it. And again, it's either the constant column or the constant matrix of this linear system up here. Okay, and then to put all this together, remember that this linear system is equivalent to this equation up here. And the left-hand side of this equation actually factors as a product of the coefficient matrix and this matrix over here, which I didn't give a name, but you can call it the variable matrix if you want. That's kind of what I've been calling it. To be honest, I'm not sure what the standard name is, but in any event, it's the column matrix that has all of your variables listed in order. So if you multiply these, you get exactly the left-hand side. So what we'll do is we'll do exactly that. We'll multiply them. So A times X, so the product of these two matrices, has to equal the constant matrix over on the right-hand side, right? Because these two multiply to this one, and this one is equal to this one. So I can say that this is equal to B. This is now a really nice, compact, and concise way to express this entire linear system. So that's why I said this is really nice. Matrix multiplication will allow us to express linear systems efficiently, and this is exactly what I meant by that. And this is called the matrix equation. Again, of that linear system that we started with. One last thing that's quite handy that I'll mention before we move on to some examples, because these are quite abstract. But what if I wrote A inside a matrix bar, and then I drew a vertical line, and then I wrote the constant column B, like that? How would you interpret that? Well, here's how you should interpret it. What this means is start writing a matrix, have it split it up with a vertical line. To the left of the vertical line, write the entries of A. To the right of the vertical line, write the entries of B. So, or in other words, the constant matrix. So what that would look like is this. Right, because these are the entries of the coefficient matrix A. And then I'm going to draw that vertical line, and then over on the right I'm going to write the entries of the constant matrix B, which were B1 and B2 over here. So I got B1, B2. And what is this? This is not anything new. This is something we've seen before. This is actually the augmented matrix of this linear system. So this is the augmented matrix. And I'm not going to underline it because it's not a new definition. We've seen augmented matrices before. What is new about this is that this gives you another way to write it more compactly. Okay, so let's look at some examples. So the first one we'll look at, I'm going to write down a system of two equations in 4 variables, because I said that this would work no matter how many equations you had and no matter how many variables you had. So I just want to do this with a couple of different examples as well to show you the pattern. So that's my first equation. And the second equation will be 2x1 plus 4x3 plus x4 is equal to -2. So that's a linear system of 2 equations and 4 variables. If I were to write its matrix equation, I would follow this guide, right? First, write the coefficient matrix. So what are the coefficients? Well, there's a 1, 2, -3. This is like a -1 coefficient. Here I've got 2. There's no x2 at all, so I've got 2, 0, 4, and 1. So let's do that. 1, 2, -3, -1. And the second row will be 2, 0, 4, and +1. So that's the coefficient matrix. What's next? Now I need to write my matrix of variables. And I'll do it the same way we did up here. Write it as a column matrix, but just list the variables in order. So you have what, x1, x2, x3, and x4. So that here it'll be a little bit taller. x1, x2, x3, and x4. And then that's the left-hand side, equals the constant column. So equals, constant column will just be the 2 constant terms put together in a column matrix. So this will be a 2x1 matrix with entries 10 and -2. So that's the idea here. These are equivalent to each other. Okay, they say the exact same thing. On the left-hand side, this is a linear system. Just to make sure we practice using the right terminology. And then on the right here, we've got a matrix equation, because it's an equation where the left and right-hand side are both matrices, right? We've got a 2x1 matrix here, and over here we've got a product of a 2x4 and a 4x1 matrix. And of course, you can check that the dimensions are compatible. 2x4, 4x1, it's going to multiply to be a 2x1 matrix. So that's the dimensions do work out, but so do the products, and these are equivalent. One last example. Let's do one where we go the other way. Let's write down an example where I start with a matrix equation now. So we'll say 5, 3, -2 for the first row. So this is really a coefficient matrix that I'm writing down here. And then 0, 4, and -1. And then, so that's the coefficient matrix. The variables are going to be x, y, and z. And then the constant column would be 0, 1, and 1. So that's a matrix equation now. Let's write down a linear system that's equivalent to it. So, well, how many equations am I going to have? Well, there's one equation for each row of the coefficient matrix, and I know what the variables are going to be. They're going to be x, y, and z. These are the coefficients in each of the respective equations, and these are the constant terms. So the first equation is going to be 5x plus 3y minus 2z, right? I'm taking this row and I'm multiplying it by this column, and that's going to get me this entry. It has to equal 0. The second equation, I'll have 0 times x, 3 times y, and 2 times z. So I might as well just write 3 times y plus 2z, and that's going to equal the second constant term, which is a 1. And then my third equation, I'll have 0x plus 4y minus 1z. So we've got 4y minus 1z is equal to 1, and then that is your linear system. So just to complete the pattern that we did in the first part, those are equivalent. This is our linear system, which we wrote down on the right, and then this over here is our matrix equation. So you can go from, if you are given a linear system, you can write down the same thing as a matrix equation, but if you're given a matrix equation, you can go back and write it as a linear system. So it works both ways. So that's how we can use matrix multiplication to really compactly and efficiently express linear systems, even if they have a lot of equations and a lot of variables.